Nicholas, it seems to me that climate scientists rang the bell. I said 30 years ago, you said probably before that there was a problem coming and that this was the data behind it. And we're now at the point where I don't think there's a lot of debate over that. But what is the role, how's the role of scientists changed? Since they're not just ringing the bell, now we're talking about finding solutions. Like, how has their role evolved?
Well, to say that they rang the bell is not to say that climate science hasn't advanced a great deal, and it's been advancing, I think, over the last couple of decades, not only because of developments in areas like artificial intelligence that allow certain kinds of scientific analysis to take place in ways that are extremely well suited for the complex systems that climate is part of, and that therefore necessitates thinking about systems theory as well as the individual kinds of measurements that have to be modeled, have to be built and modeled, and then thought about in relationship to so much else that's going on. But it is certainly the case that I think there is, and has been for some time, a consensus about what and how scientists think about the relationship between greenhouse gases, between the use of fossil fuel, between changes in our atmosphere, and climate change, and not just the rise of temperatures, but the changing character of our weather patterns and all the rest of it. Now, just as a way of saying that when you have a community of scientists, you're going to have disagreement. There is consensus. There are some people who don't buy the consensus. I actually have a good friend who's a very distinguished physicist, used to be the provost at Caltech, who wrote a book called Unsettled just a few years ago, in which he basically goes through a lot of the science in climate science and argues that there are still lots of unsettled issues. But the interesting thing is when you read it through, you realize that it's a physicist thinking about certainty in a way that is actually quite different than what is part of the development of climate science, which in some sense is a very recent science, because even though in the 19th century, Alexander von Humboldt and others were thinking about natural history as a totality and actually believed in the idea of the Anthropocene well before we began using the term, because it was natural history, human history, all tied up together. Still, I think the point about what we're dealing with here is that science tells us a lot of different things, but there's a lot we don't know. And
that's
so
what makes people uncomfortable.
That is exactly what makes people worried about the future, both from the point of view of possible extinction risk, and from the point of view of those who simply can't quite believe that our world as we know it today is going to change so fundamentally. But your question really is about the relationship between science and
the
solutions, public,
yeah.
and both policy solutions, but also the acceptance of these solutions. And that's a really troubling question. And in an odd way, the last 5 years, we've all experienced something that really seems so counterintuitive, which is a growing distrust in science. I started my role at the New York Academy of Sciences in the spring of 2020. I did most of that first year out here in California, which was actually quite nice. But aside from that, of course, one of the things that we focused on at the Academy was identifying the virus, understanding it, how did it get transmitted, and we saw, in real time, science at work. And we also saw that science changed its mind. And although there were those calling for us simply to follow the science, some people felt that that was actually a very zigzaggy route. And I think the fact that we saw a changing scientific consensus in a very compressed way, and then the kinds of reactions to it, and even today, along with the news about everything else, you still have in the New York Times kind of almost regular stories about how public health officials got it wrong. You realize that we're in a moment in our history when science, in some sense, has never been more powerful, closer to certain kinds of truths, and yet most distrusted and subject to the kind of skepticism that we see we see as a more and more pervasive thing, both in this country and around the world.
At the same time, one of the other things we talked about, there was a story in the Times this weekend about engineering our way out of the climate crisis. There are probably a great number of engineers in the room. We're in Silicon Valley. There is an engineering mindset that takes hold here, which I think is wonderful and is definitely going to be part of the solution. But maybe talk a little bit about how you react to that article and the solutions that were inside of it.
Yeah, no, it was an incredibly interesting article. And of course, it focused primarily on carbon sequestration, which is something that that serious people have been talking about for a very long time. How can we actually develop means of carbon capture that would deal with the present crisis, which is to say you can stop burning fossil fuels today, and they're not going to go away anytime soon. There's a very long life that they're going to have, and the effects that go along with that will continue to unfold regardless. So very serious people are talking about that. And very serious people have also been talking about solar geoengineering or solar radiation modification, SRM. So
you got to explain what that means, because solar, it's pretty fascinating.
Well, let me just say two things. First, the piece in the Times about Occidental in Texas and Climeworks in Iceland. And I actually went to Iceland last summer. I don't know how many of you have been there. It's an amazing place to go. And there's a lot of geothermal energy, and you can see it just about everywhere. And it's being used, obviously, to engage this incredibly ambitious project to capture huge amounts of carbon and then sink it deep in the earth and effectively to make it reform as part of the bedrock of our interior earth. And to that extent, it seems like a great thing. But as the Times went on to say, even as the kinds of currently projected developments take place, it'll be a fraction of the overall production of carbon, and it will only reverse to a very limited extent what's going on. And there are many people who are worried not just about the possible uses of carbon sequestration to use the mechanisms effectively to produce more oil, but also that there might be this sense that new technological interventions will actually begin to take away from the single-minded attention we have to give to an energy transition, to stopping our burning of fossil fuels, to not really think about renewable energy with the same degree of urgency that we currently do. And nowhere, in a way, is that more striking than in this solar radiation modification. So some of you know that that we've had some major volcanic eruptions in human history. Most recently, Mount Pinatubo erupted in the Philippines in 1991. And over the course of the next year, global temperatures actually reduced by about 0.5 degrees centigrade. Krakatoa, late 19th century, according to some estimates, the measurements were less precise at that point, but nevertheless, according to some estimates, global temperatures went down. No, but they went down, some say, as much as 1.5 degrees centigrade, which of course is the magic tipping point for all of what we're trying to do with respect to the current situation. So what this involves is effectively replicating a volcanic eruption, spraying aerosols of sulfur dioxide into the upper atmosphere, and effectively reducing the amount of solar energy that penetrates into our atmosphere, into the Earth. There are others who see solar radiation modification as effectively putting some kind of coating on the top of clouds to reflect the sun's energy and heat. But the idea is that if our biggest concern is keeping global temperatures under that 1.5 degrees centigrade threshold, this would be a quick technological way to do so. Sounds great.
It sounds and monstrous somehow at the same time. Like, as a scientist, is this a serious option?
So, first of all, the problem here is not just that it just takes one metric as its object, right? So it's only about reducing global temperatures. It's not necessarily, and we certainly don't understand, and scientists don't have really very sophisticated ways to understand this apart from actually doing this, which is an odd way to do an experiment on the world. because if it fails, the consequences would not be so good. But scientists don't understand, what is this going to do to localized, to regional weather systems? What will it do to monsoon systems? What will it do to islands that really can't absorb any significant levels of sea rise before just literally going underwater? And there are many, many concerns that this is a kind of idea of technology driven by a kind of techno-optimist Western elite that really doesn't think about the implications of climate change for all parts of the world that are much more vulnerable, much more on the edge, and likely one way or the other to suffer effects of climate change much more dramatically and drastically even. So there's a lot of concern about trying to find ways to model what this would do and to get more scientific understanding of what that process might entail without actually doing it. But so far, nobody's figured out, how to actually model this in a way that has any real degree of scientific authority attached to it.
So this is where, we would try and use, this is a technological solution to a very complex problem. We've got a new technology that's just rolling out or has been around for a while but is now being popularized. Would AI allow scientists to give them the tools to build these types of complex models? And how confident are you that that's going to be a game changer?
So again, first, always have to do the two sides of the coin. Coins have many, many sides, but here there are two sides that we can point to. One is AI is going to be a game changer. AI takes a huge amount of power, energy to run. And there was another piece recently in the New Yorker about this, if you saw that, just summarizing some of the recent estimates about the amount of energy that is actually required to support generative AI. And the chat GPTs and LLMs that we all know and love today. And estimates go from very small countries to countries as big as Japan over the next 5 to 10 years. That is to say, as much energy will be needed for AI as powers the entire nation of Japan in 5 to 10 years. That being said, AI is indeed an extraordinary resource for developing much more sophisticated ideas of modeling. Again, these are climate is a very complex system, and in complex systems you can move some of the the numbers just a little bit this way or that way, and it's going to have dramatic effects. And we all saw that with the curves that went around infection rates and potential mortality rates in the pandemic, when you just took assumptions and you moved them really by what would seem to be very minor degrees of latitude, and then see the huge effects downstream in terms of what actually develops. But modeling will certainly get better. But that's not all AI can do. AI is going to be, I think, and we've been hosting a whole series of conferences at the New York Academy on this question, bringing together scientists from a lot of different fields. AI is going to be a huge resource for scientific discovery and development. We know this to be the case in biomedical science, leaving aside the kind of extraordinary capacity that AI has to read things like scans and X-rays and so on and so forth. It's going to help scientists discover new drugs, and it's going to potentially help them develop, without having to go through full clinical trials in a real population, new kinds of therapies for cancer and just about every other kind of disease. And this is, just the tip of the iceberg in a way. But in climate, AI has the capacity, among other things, to help us understand and discover, really, new materials that will be extraordinarily important in the energy transition. For example, I was talking to a material scientist yesterday who's on our board at the Academy, who was talking about a series of papers that have been done on the use of AI to look at diamonds and how diamonds might, in fact, be as useful as silicon for new generations of semiconductor building. And this could be a huge change. Now, of course, we all know that the energy transition is to a very large extent dependent on particular kinds of minerals, and lithium is at the top of the list. And there are issues around everything from the amount of pollution and energy that goes into mining these precious metals, but also, of course, their environmental impact after they've lived their life inside the hood of a Tesla. And we know we have to both diversify and potentially find new ways to power the energy transition. And AI is, I think, going to play a very powerful role in doing that. But we have to figure out either how to take the heat that is generated from these mega electricity stations that power AI for other kinds of purposes, or really find a completely different way to think about how AI is going to help us solve a problem that it's, of course, contributing to in a major way.
Yeah. Well, I'm happy to hear this opening, because we are going to have conversations about batteries and recycling. We're going to have conversations about AI coming up very soon. But it seems to me that there's a core communication problem here, whereas as a scientist, you're used to the variety and the uncertainty that comes as science as a process, there's no single way to chart your way through it. But that seems like it gets to the fundamental problem where there is a lot of distrust. As you're working with scientists and you're doing work, like how do you cut to the chase there? How do you improve those communication skills so that the message is more clear?
So I'll answer that, or at least I'll attempt to answer that, but I want to say just one thing first about some of the work we're doing at the New York Academy of Sciences. I want to make sure I say this, because it's something that is an effort to bring people together, to use the resources of science to really think through these kinds of questions more broadly. We developed in the early days of the pandemic something called the International Science Reserve, and it came out of an effort that, in fact, was spawned at IBM that involved the High Performance Computing Consortium, effectively taking donated surplus computational capacity in places like DOE labs or major tech companies or large universities, and devoting a certain amount of that capacity pro bono to projects that were directed towards trying to solve in a very short term some of the immediate issues around the pandemic. One of the things that came out of that effort, for example, was the way in which ventilators could be used for more than a single patient back in the really dark days of the early pandemic. And there were people who had laboratories and were doing work. They couldn't get funded for pandemic-related things because there's this long time cycle to applying for NSF or NIH grants. And they certainly couldn't purchase the kind of computational resource time and facilities they needed to test out the ideas that they wanted to deploy in real time very, very quickly. So we developed the idea of the International Science Reserve basically to bring together scientists across very many different fields and from around the world, which is why the international is part of the name, in order to really think about how to be better prepared the next time around. And we know that one of our big problems is that when we don't have a crisis, we prefer to think it's not really going to happen. Certainly it's not going to happen anytime soon. It's relevant to climate as well, because of course it's easy to kick the can down the road. That's what we do a lot. But in short order, it turned out that we moved the focus of the International Science Reserve from mostly pandemic-related kinds of preoccupations and activities, and we did scenario planning exercises, et cetera, that were actually meant to test the network and see how prepared we might be for, say, a waterborne virus that might spawn a pandemic somewhere, or some other kind of version that it would be very different in terms of pandemic response. But found that, of course, almost all of our attention began to be focused on climate, and we did scenario exercises on wildfire, on floods, and other things that are obviously related to the weather effects of climate-generated change more broadly. And in that context, we really found that it was interesting how many scientists from all over the world were interested in working together, but didn't have the normal mechanisms that they needed to establish the networks that would really allow them to figure out who might be useful in the event of a wildfire developing in a transnational context where they weren't able to simply resort to the normal modes of either response or finding out the kind of data you would need, even about things like the movement of pollution. And we saw that, again, in real time with the wildfires we had first here in California and then, of course, in Canada last year. So this is something we're doing, and we'd love to get we have support from IBM, from Pfizer, from Google, from UL, but we need many more people to get involved. It's a completely pro bono operation. We run it out of a very small office in New York, but it's meant to really develop a kind of network capacity for doing this kind of work. Now, one of the things we also are doing as part of this is to try to bring scientists together to help them understand how better to talk about what they do. It's very easy to think that if you just put a few graphs on the whiteboard or on the screen, that you can persuade people that pandemics are real, that masks actually do work, at least in certain kinds of circumstances and so on, or that climate change is real and it's going to affect us. And I think one of the things that we've found over the last few years is there's this kind of crisis fatigue. So you have, on the one hand, people who are talking about extinction risk with respect to not just climate, but even AI. And on the other, people who are saying, I just can't keep all these, I just can't do this. And the scientists will say this, but it was really cold last week, and there's snow in Boston today. What are we talking about? So we do work with scientists, but we also, of course, know that at the end of the day, it's going to be about creating incentives, creating real ways in which the consensus about climate change is going to be exemplified in the ways corporations work and the way government supports things like everything from replacing, as I'm actually doing this week, old and dysfunctional solar panels on my roof, having the subsidies that we need in order to see the economic payoffs, and at the same time have some sense, along with the growing worries and even talk about doom, some sense that we're making progress. If we don't have that, people are going to check out, and that would be the worst possible outcome altogether.
Agreed. I think we're going to leave it there. You're going to be around with us all day, so you'll be part of our ongoing conversations. But thank you so much for talking to us today.
Dan, great to talk to you. Great to be here. Thank you all.
Thank you.